Welcome, Urvaksh.
Hey, so I'm Irani and I'm at the Gear Lab at MIT with Amanda and Nina. And I'm going to talk about the design of a passive prosthetic foot that is mass manufacturable and also globally distributable. And I'll get to what that means in a minute. And also the work is focusing on low and middle income countries, and everything I'm doing is transtibial, so nothing above the knee. And just to give everyone a bit of background, roughly 80% of the world's transtibial amputees live in low and middle income countries. And a majority of these amputations have been caused due to trauma rather than like health-related issues like diabetes. And this leads to a bunch of healthy young individuals that would have been prescribed K3 or K4 feet in the US. But the annual healthcare expenditure in low and middle income countries per capita is less than the average cost of a single ESR foot in the US, and significantly less. So to give you an example, like it's $30 per capita per year in India, and the average cost of an energy storage and return foot in the US is roughly $3,000. So like 2 orders of magnitude less. And this forces amputees to settle for low-performing feet that are not suited to them. So satch feet, which is like a solid ankle cushion heel, which is usually prescribed to old people or people with lower mobility. And so there's this clear unmet need for affordable energy storage and return feet. And that is just the cost performance curve of the current market. And what we are trying to do is kind of shift down here and get into this space where we get the performance of these passive ESR feet, the carbon fiber ones, but still meet the cost of these conventional feet. And so to tackle this issue of developing a low-cost foot, the Gear Lab has come up with this metric called the LLTE, or the lower leg trajectory error. And essentially this is just a metric that allows us to connect a foot's mechanical design to its biomechanical performance. And it's just a root mean square error, and what we do is we say if we have the constitutive model of a foot, which means if I push on it and I know how it bends, I can apply able-bodied loading to it and then see how the foot deforms, predict the knee location, and from there go ahead and I have the lower leg orientation, and that tells me how far my lower leg orientation is from able-bodied. So that's essentially what the LLTE metric tells me. It tells me how far I am from able-bodied gait. So as you can imagine, an LLTE of 0 means that I have perfectly replicated able-bodied gait. And using that metric, what we've done is we've gone ahead and got the LLTE design framework. And what we do here is we have this parameterization of the foot. The red variables are the independent ones. So there's 12 independent variables, and we tweak these. And we run an optimization, a topology optimization that gives us the structure of this foot. And we optimize its stiffness to have the lowest LLTE possible, while also satisfying stress constraints. And this basically means we make sure it doesn't yield or break. And these LLTE feet have been tested in gait labs and in the field in India, and they've performed brilliantly. So we've got our quantitative measures, which is our total deviation from able body, and that works beautifully. And we've also got qualitative feedback from participants in the field trial, and as you can see, they were either as good or better than these $3,000 carbon fiber feet. But the problem is that all of these feet that we've tested in the past were prototypes. They were not mass manufacturable, so they had to be machined, and this could take on the order of days and cost roughly $200. So we make our feet out of nylon, and that foot up there costs roughly like $10 of nylon. But so the material costs are $10, but the manufacturing cost could go well over $200, just because they had to be CNC, and it would take a lot of time and labor and so on. And another major problem we faced is that the feet we tested were only compatible with a single attachment system. So they had to be attached to the rest of the body using wood screws in that case. That's what that big block up there is for, or a pyramid adapter. And yep. So essentially we couldn't distribute through any clinic or any distributor that wanted to use different attachment systems. And these are just 2 examples of popular attachment systems. So that's the ICRC attachment system, which is the red cross, and on the right is a pyramid adapter. And so we had to upgrade our design to be mass manufacturable, but we also wanted the original performance of those solid feet that we had. So we've gone ahead and made it injection moldable. And for those of you who aren't familiar with injection molding, it's used to make like every thin plastic thing. So you have like Happy Meal toys, water bottles, Legos, everything. And the major constraint that you need for injection molding, there's a bunch of constraints, but the major tricky one is you need uniform cross sections, and for nylon 6/6, they can't be thicker than 4 millimeters. So we had to somehow get a shape that would give us 4 millimeter thickness, but still maintain our original stiffness and our original strength. So we went ahead and used C channels, which are commonly used in construction because of their very, very high strength and bending. And yep, we also have this split down the middle that gives us coronal compliance. So when someone steps on a stone or something like that, yeah, we have coronal compliance. And I'm running out of time, but if anyone has questions, I can get to them later. And we've gone ahead and run our optimization with this new architecture. And this has given us an LLTE value of 0.1. And just to give you all context of what that means, the feet that we've tested in the past, we have tested feet with roughly 0.1 LLTE values, and they have performed brilliantly. So we have, with our new architecture, we still get that same LLTE, even though we have this small strength compromise, which is roughly 90% of our original strength. We've gone ahead and validated our constitutive model. So we know that the LLTE is actually 0.1. So we've gone ahead and done Instron mechanical tests, and we're like, okay, it matches exactly what our model says. And the mass of this foot is roughly 200 grams without this foam overmolding. So we're going to overmold this final keel with a ruggedized foam to be waterproof for reasons that we'll get into. And yeah, so in conclusion, we have this ruggedized, injection molded, energy storage and return foot that can closely replicate cable body tape. And this is roughly $5 of nylon, and it costs $5 of nylon in the US. And yeah, so that's what we have. And for future work, we're planning a field trial, and we're also going to get like a product line, kind of like shoes, because this was optimized for a very specific patient, but we're going to get a discrete number of sizes that would be good enough for the majority of the population. Yep, that's it.
2 minutes for question with Rowan.
Thanks for the presentation. I really enjoyed that. I love, so you're optimizing the design, and I think a lot of those optimal controls folks have big dreams of helping you, eventually helping you optimize the design. But like, I have a platonic ideal as to what I want to do with that. But what do you actually need? You're actually doing this in optimizing design. But like, what are the things that we can help with that are actually useful to you?
So just to make sure I understand the question correctly, are you asking about what I need to run my optimization, or what I need from controls?
What are your next needs after this? Like what are your pain points currently that you're like, man, I really wish I had a better optimizer did blank.
Okay, so that's a pretty question, but one pain point that, what we would ideally like to do is approach that LLTE value of 0, like I said, sort of perfectly replicate cable body tape. And right now, our designs that are optimal are stress constrained. And what that means is, we could get a lower LLTE if we had a stronger material that could bend a lot but not yield. So, or the other way to go about it is have a broader foot. So as you can imagine, as I increase the width of my foot, I can handle more and more stresses without yielding. So currently, we're trying to fit inside the Jaipur foot overmold, and the Jaipur foot is one of the most commonly distributed. It is the most commonly distributed foot in India, and we're trying to fit inside that overmold because a lot of amputees, there's this stigma of wanting to have like natural looking feet, is how they go about saying it. So I guess the major pain point is if we could get a cheap material, but we've done a bunch of, like we've looked through a lot, and nylon 6/6 seems to be the best in terms of handling you. I don't know if that answered the question.
Good enough for me, thank you.
Very nice work and very impressive results. The one question I still have is like for your optimization, what kind of dynamic inputs for the knee side are you taking, and are they adapted for subjects?
Okay, so what we're doing is we're essentially applying able body loading for ground reaction forces, and that's our assumption. So we say eventually when we get to a low LLTE, what we do is we say we want to match able-bodied kinematics, and if we do that, we will match able-bodied kinetics. So, and we've tested that as well. So once we get a low LLTE, we've gone ahead and tested that we get, so to answer your question, the inputs that we use are just able-bodied ground reaction forces, and it's a
But what is on the knee side? Like, in your plot, you show like
Oh, it's-
forces and knee forces.
it's constrained. So what we do is we have, let me, I guess from the knee side we make sure we're using quasi-static, the quasi-static assumption. So if we have, let's say, I don't know, 10 newtons in Y, what, 5 newtons in X, we constrain the top of our foot to match those and match the moment as well. So we say this is in static equilibrium, and because of the pace we're walking at, it turns out to be that it's a good assumption, which we tested.
Brian, last question.
Yeah, I guess I don't know if this is true or not, but with a passive device, are you able to ever perfectly replicate like the kinetics of able-bodied?
I don't think so, no.
And follow-up question, what is the motivation for having able-bodied kinematics as the goal? Like, is there maybe another goal, and what are your thoughts on that?
So initially, the way the project started out was, again, we were going and we conducted a bunch of stakeholder interviews. So we interviewed amputees in development countries, but India, solely India. And all of them, literally like over 90% of them would say, hey, all we want to do is look normal. So when I wear jeans or when I wear long pants, I want no one to know that I have an amputation. Like I don't want anyone to know that I'm wearing a prosthetic, which also motivates the need for the foam to have like this. And they want like really detailed toenails and things like that, so that it's as inconspicuous as possible. So that was the primary motivation. And we also assumed that if someone walks with able-bodied kinematics and kinetics, it would be more comfortable for them. And that's what our results showed as well. Like when we went through a modified like DEQ, all the subjects were like, hey, this feels great.
Thanks.
Thank you.